months ago.
Okay, the firing line, please.
He'll try to blow a hole in a 5-ton model dam. The massive bomb required to break a full-size dam scales down to just 2 ounces of plastic explosive for Sydney's test. He suspends the explosive in the water several feet from the dam wall.
4, 3, 2, 1. Good dam.
The dam survives. Sydney realizes he must move the explosive closer to the wall to have any chance of breaking it.
2, 1. We've knocked the parapets off. That doesn't matter structurally, but we've made one vertical crack from top to bottom. I'm not a structural engineer, but my guess is that is not beyond hope. It might be possible to patch it up, but it is seriously weakened. But it is not catastrophic failure.
As long as there is water between the dam and the explosive, the dam remains intact. Like Wallace, Sydney has discovered that the secret to dam busting is putting the charge in direct contact with the dam face. This allows the mass of water behind the charge to focus the resulting shockwave onto the dam wall.
2, 1. That is semi-catastrophic.
It took Wallace more than a year of experimenting. Before he himself achieved a small-scale catastrophic result. Now, he was ready to tackle a real dam. He found what he wanted hidden away in a Welsh forest. The Nanty Grow Dam was 5 times smaller than the Muna, but it was as close to the real thing as he could get. This is actual footage of Wallace observing the test. His team attached their explosives to the dam wall. Success. Wallace now knew his bomb needed to explode in contact with the dam wall to inflict maximum damage. But he had to devise a way to deliver his weapon precisely to that spot from a moving airplane. Dropping the bomb from directly above the dams would not be accurate enough. Then, Wallace had a revelation. He recalled reading about a tactic used in 18th century sea battles called skip shot. Naval gunners looking to pierce the hull of an enemy ship would skip their cannonballs over the surface of the water. Could skipping his bomb into the dam wall be the best delivery method? Armed with a bag of his daughter's marbles and a homemade catapult, he began working on the physics of the problem in his own backyard. He recruited his 16-year-old son, Barnes Jr., to be his research assistant.
Look, the distance between that bolt...
60 years later, Barnes Jr. revisits the experiment with an assistant of his own and finds out for himself how hard it is to bounce a marble off water.
And so you want that not more than 3 inches above the water. Get the thing... Oh, there we go. Right, you want to get it not much more than... not much higher than that. It's not even... If you give me something with centimetres on it, you can think again. It's inches.
It's 3/4 of an inch.
Yes. All right, okay. 3/4 added to... Oh, well, go on, farther down thing and see what happens. I think it's worse than it.
Was that worse? Was that
It was
worse?
almost identically the same.
Same place?
Yep. Almost exactly.
See, what we want it to do is bounce in the middle, don't we?
Yes! Right, now.
Barnes Jr. discovers the angle of entry needs to be precise, no greater than 7 degrees off the horizontal. Otherwise, the marbles don't bounce, they sink. Like his dad, Barnes Jr. goes through a big bag of marbles before he gets his desired result.
3, 2, 1.
Way, it works!
Barnes Wallace Sr. had bounced his marbles off water. He now had to construct bombs that would do the same. What's more, they would have to bounce far enough to allow the bombers to get away before the bombs exploded. Wallace built a larger catapult and set it up at a lake near his office. He chose balls made of materials ranging from lead to balsa wood. He then had them engraved with grooves and dimples of various shapes and sizes. Wallace enlisted the help of Amy Gentry, his secretary, to track the success of the experiment.
She was a national rower, oarsman with the Ladies Rowing Club, which is a cheerful lady. And when she was in the rowing boat and old Wallace stood up to do something, get his catapult right or something, she said, "Sit down, Wallace, I'm in charge of this boat and we don't want us both in the water."
It was on that lake that Wallace made a critical discovery. Dimpled balls bounced the furthest. The reason is found within an aerodynamic premise that today drives an entire industry: the quest for the perfect golf ball.
Well, this is Iron Byron. This is our mechanical golfer that we've used since 1976 to test golf balls for overall distance. Well, the beauty is that Iron Byron is very repeatable. He'll hit the same golf ball again and again, 109 mile an hour club head speed every time, unlike golfers who get tired, who maybe aren't the same today as they were yesterday.
When struck by Iron Byron, a dimpled ball travels up to 300 yards.
Stan's going to put a smooth golf ball on the tee. The smooth ball has no dimples, but in every other respect, it's identical to a regular golf ball.
A smooth ball travels only half the distance of the dimpled one.
The trajectory will be less stable. It'll hook and slice a lot more than the dimpled ball would have.
The friction a smooth ball creates as it flies through the air leaves a big wake, which slows the ball down. Dimples stir up the air flowing over the ball, diminishing friction. Air currents stick to the ball for longer, creating lift. With less resistance, the ball travels significantly further. Wallace had figured out the ideal shape that would allow his bombs to get to the dam, but he now had to ensure they wouldn't bounce off and end up too far away to do any damage. So he